I don't know, do you think this filament might be wet? I've stored it with the silica gel, so it should be fine, right? Let's go. This video is sponsored by Sunlu and their new SP2 dryer system, which I'm going to be showing you throughout this video because it's on topic. But do bear that in mind, this is a dryer you'll be seeing used for demonstrations, and I do appreciate Sunlu agreeing to do this when I reached out to them with the proposal. They were the first I asked, because I use the S4 a lot. So why am I doing this anyway? It's pretty simple. I see people misunderstanding the topic a lot. The topic of humidity and wet filament. All the time, and I find it frustrating, but at the same time, I find it entirely understandable. At the root of the topic of humidity is some basic, easily understandable concepts, but if you don't get those, things above that don't make sense. Hopefully, by the end of this video, the vast majority of you who are actually listening and not asleep will learn at least something. The most logical place to start is explaining what wet filament is and what it isn't, and why you should care at all. Wet filament is filament that contains enough water to cause it to malfunction. The wording is chosen not that carefully, but carefully enough. Dry filament, for all practical purposes, does not exist, and hopefully by the end of this video you'll understand why. This does lead us to one of the first concepts you're going to repeatedly encounter in this discussion, though. Most filaments, I would say all of them, but there's probably some obscure materials out there, like glass. All the plastics that you're going to encounter in everyday 3D printing are inherently hygroscopic to very varying extents, but they're all inherently hygroscopic. They will naturally hog water molecules given any chance, and it's impractical to get rid of all of that water. You see, filament performs adequately when dry enough, and what dry enough means is surprisingly hard to pin down, but a decent starting point seems to be in equilibrium with an environment below 20% relative humidity, which might seem like a complicated thing to say, because it's not even accurate. It is a complicated thing to say. It's just what works for nearly every filament. If you follow that rule of storing your filament in an environment below 20% relative humidity, and it's never been in one higher, then it will print fine. In fact, PLA or ABS are going to be fine in equilibrium with an environment below low 40s relative humidity, which is probably why a lot of us don't have moisture issues with PLA, because our houses generally are that in this modern day with air conditioning, central heating, depending on where you live. And so was mine. It was about 40 to 45% relative humidity here until I got a fish tank, which honestly wasn't the smartest thing to do. But that just goes to show, just a change like having plants in your room or a fish tank can massively raise the relative humidity. That's definitely beyond the scope of this conversation though. What wet filament does to a print can range from quite insidious to positively blatant. And as such, if you're trying to find a filament that's wet to get an example of what you're looking for, it's usually quite hard, because sometimes filament can be completely wet and not show any signs. Sometimes it can just print terribly and not be wet. The problem is that there can be other reasons for almost every symptom of wet filament. Stringing, for example, could be moisture or a dozen other print settings. If you hear filament popping or smoking, that's a sure sign that it's wet, or it could just be too hot and it could be burning, and so on. The best solution to the problem of wet filament and detecting it is to not have it in the first place. So it's prevention and good filament management. And before you could do that, I would suggest getting a really good grasp of the environment you're working with. What is your room like? Do you have a fish tank? Does the humidity change, or is it stable? So why am I saying it like that? Why am I using words like in equilibrium? Well, if you put a wet thing, like, say, hanging laundry up in a room or putting a damp bit of bog roll in an environment like air, it will dry out, but it doesn't instantly dry out, does it? What is happening in the process of drying is that there's molecules of water in the wet thing, but there's also, unsurprisingly, molecules of water in the medium the wet thing is in, i.e. the air. None of these molecules are particularly sedentary. They're all bouncing around, smacking into each other, and the ones in the air will be bumping into the wet thing. Sure, some of them will stick to it. The ones on the wet thing will be thrown off into the air, and they'll never come back. They'll just remain in the air. But there is this term that we need to introduce. It's called vapor pressure, and it means kind of exactly what it sounds like. There is considered to be a higher vapor pressure in the wet thing that's drying than there is in the air surrounding it. That's why it wants to equalize. So if you take that wet filament and you put it in a dry environment, then The vapor pressure difference is what will make the filament overall drier than it was, and it will make the air around the filament overall wetter than it was, until you get an equilibrium. But the TLDR is that everything is trying to reach an equilibrium in terms of how much water it's got in it. If you add some desiccant into the mix, the desiccant will have a lower vapor pressure than the air, and it wants those water molecules, and it has a huge affinity for water molecules. So you've introduced kind of a gradient now. The silica gel will want to create an equilibrium with the air, and then guess what? The air gets drier as a result. Now the air is looking for a new equilibrium with the filament because the air is now drier than the filament, so it's going to then dry out the filament. For clarity, the silica gel isn't directly drying the filament. The silica gel is drying the air around the silica gel. The air is then obviously circulating, and the air is drying the filament. This continues until, surprise, surprise, all these three items are in equilibrium. So we did a poll with interesting results. I think it kind of was a trick question. The answer is it is complicated, as you hopefully will see now. The theoretical answer, of course, is that the silica gel will work if you have enough time and enough silica gel. This is consistent with the physics, and I think for some filaments you will actually get away with just using silica gel if you leave it for a week or two. But let's do some experiments first, so I can explain how relative humidity works, because, yeah, that's a thing. I have here a box of air. It is just air, and the box is airtight, which means it will continue to be the same air inside the box. We're not condensing the water vapor, we're not setting fire to it. It's going to stay in the box, and the same amount of water vapor is going to stay in the box throughout the entire experiment. At least I hope so. So whatever we do to this sealed box, the amount of water inside the sealed box will remain the same. This time it's not a trick question. If we look at the graph of what happens to the relative humidity of the air in this box, we can see the temperature changes for a start, and that's because I've done that. I've changed the temperature. But remember, the box is still sealed. It's still the same amount of water in this box. Can't leave. So why does the humidity go down when the box gets warmer, and why does the humidity go up when the box gets colder? We are not introducing more water. We're not teleporting any more water in here. Most of you can probably immediately answer this question when I ask it in this manner, but a good proportion of the same, most of you, are probably running your filament dryer with the lid closed. Take a moment to think about that. We'll come back to this. I'm surprised to see that there are some rather enthusiastic opinions on which desiccant choices people are making. Apparently, a minority of viewers have decided that silica gel is not good enough for everyday desiccation purposes anymore. Indeed, can you even call yourself truly desiccated to the hobby if you're, I quote, still using silica gel? I don't want to waste a lot of time discussing this because it's ridiculous. It's not what the video is about, but given the bar is pretty low for the humidity requirements to stably store PLA, and still even hygroscopic filaments only need to be stored below, say, 20%, and these numbers are well within the ranges that the cheap and plentiful silica gel are happy to work within, well, if you want to use these other ones, I presume they cost more. I can't really get them here, or not easily. Fine, I get it. You probably mail order coffee as well, because you think the supermarket stuff isn't good enough. You're probably right there, but I drink instant. That is fine, I have no problem with this. But, as you can see in the survey, most people use silica gel. That is fine. It's also worth noting that silica gel is a very easy desiccant to work with. Some of them don't lend themselves to being readily recharged at temperatures that we can do in a dryer, for example. And some of them actually only work once, and the amount of water that they could store varies as well. But the main reason I've been using silica gel, as well as it being cheap and easy to get hold of, is that it has these indicators. Let's talk about these indicators because, well, it turns out that's a thing. The official line on these indicators is that if you want the non-toxic ones, which are, by the way, still toxic, these turn from yellow or orange to green. But that's clearly not always the case, as these ones I have definitely are not turning green. The actual chemical used is called methyl violet. Yeah, that's a can of worms, but they turn all sorts of colours, and they look really cool, so I guess we'll take a moment to watch them. And there's something cool to talk about here as well. See if you can spot it if you look carefully. Did you notice that they change when they absorb water? Not just the colour, but well, for want of a better word, the optics. I believe what's going on here, because there's not much else that can be going on here, I believe that as these beads take on more water, they become less silica and air, and more silica and water. And if you think about it, water has a different refractive index to air. So what we get is, well, we get this change of view. There's never a lack of surprises when you look close up at things. Interestingly, the indicator on the silica gel isn't fully in sync with the actual adsorption capacity of the gel itself, so if you're drying it as soon as it changes colour, you're apparently drying it when it's only 30 to 40% used up. It does look really cool, so I would still buy the indicated stuff anyway. In fact, what I actually like is the stuff that's mostly clear with the odd indicator bead in it. The best indicator that your silica gel needs replacing is when it's no longer drying the air. So if you use it in conjunction with a meter, then basically read the meter. So back to our box of air, which still has the same amount of moisture in it because I still haven't opened it, and unless it leaks, and it can't possibly leak because it cost me 85 pence. But the reason the RH is changing in here is exactly the reason you were yelling at the screen a moment ago. Relative humidity is relative to temperature. The principle is simple, but the effects can be confusing. Let me spell it out. Cold air can't hold much water. Hot air can. Quite a bit more water, actually. So what your meter is telling you is that at 20 degrees C, the air in that box is something like half saturated, but raise that temperature to just 25 degrees C, and there's a lot more room for water in that air. It's still got the same water in it, but it's a lot less relatively humid. This is important to understand, so that's why I keep hammering it home again and again. Warming up the same air without doing anything to it will lower the relative humidity, and that is the final time I'm going to explain that. So anyway, let's do some more experiments. It's about time. I've got some silica gel beads in a tray. I'm weighing them. I'm putting one of them in a sealed container with a wet bit of bog roll. That's English for bath tissue, by the way. I'm putting that... I know you don't call it that. I'm putting that aside, and I'm putting another tray of silica gel beads in just air, ambient air. Why? Well, you tell me. I'll give you 2.8 seconds to guess which one of these will gain more weight after a few hours. The idea is I want to show you that when you have a higher vapor pressure, you get more transfer of water molecules. So that is actually true, because even free air with its basically infinite amount of water has a lower vapor pressure than the box where I tried to saturate the air. I know that sounds confusing. I'll try and make that a little bit simpler. If you have a very wet thing, it transfers moisture faster than a thing that's only slightly wet. That's what that experiment was showing. The second part of where I'm going with this narrative is by putting two trays of indicator silica gel next to each other on a desk. The difference between these two is that the left one has a fan pointing at it. The right one is just in still air. I won't even give you any time to think about this because it's obvious that increasing the airflow will replace the newly water vacated air more efficiently, but the difference is quite notable after just a couple of hours. And I think that was probably my favourite experiment because it's visual. If we join these dots with a third dot though, and that dot is about how much energy the water molecules have, you can get yourself to this conclusion. If you heat up the filament, and you have silica gel in the container as well, and the container is sealed, it should dry, and it should dry quite efficiently. Right? Okay, so this round of experiments involves taking a reel of filament and putting it in a closed container. Not that one. I had to spend £7 on this one. The cube law clearly applies to airtight box pricing. So I only bought one of these, and I wish I bought more, but whatever. In goes a meter and some silica gel, quite a lot of silica gel, about 50 grams. Now, this is where we digress again, because there's a lot going on here, and it all kind of intersects. You see, you can't weigh filament before and after drying. You can weigh filament before and after drying, nothing's stopping you, but you can't, not accurately, not with most scales that you probably own, and certainly none that I own. You have an 1100 gram reel, 1.1 kilograms, including the weight of the reel, and do you know what percentage of that will be water, even when the filament is completely wet? I'll give you exactly one sponsor segment to think about this. How much percentage of water does a reel of filament typically hold? So you may have already met the Sunlu SP2. It's a modular filament drying system, and it consists of a drying base which has a PTC heater in it, and it uses forced air, which we already know is good, and the boxes that fit in place on top of it. The primary benefit of a system like this is that you have a part that you can buy for cheaper, the storage for the filaments, that you need a lot of. It doesn't contain the heater, but it does contain the filament in an airtight manner, because these bits push on after you take it off the heater, and with the plugs in and the lid on, it's actually quite airtight. So if you store some silica gel in there too as a buffer, you can put some PTFE out of this and print away, and your filament will remain dry, and you can use the dryer base to dry a different box of filament. And I'm assuming that they will sell the boxes separately to the base. Each box holds 2 reels or 1 big reel, and that's 2 kilogram or 3 kilogram, apparently, or actually anything you want if it fits in there and doesn't block the vents. So you can put your wet shoes in there if you want, but if you do, open a window, not to let the humidity out. This system should be released by the time this video comes out, because I'm late as usual to finish, so check the links below and make sure you get hold of it, because I think it might be quite popular, especially for you filament hoarders out there. Anyway, thank you Sunlu for sponsoring this extremely on-topic video. Now, how many percent did you guess for saturated stringing popping filament? If you said anything above about 1%, you're probably wrong. It isn't well defined, and it depends on the material, and you've got the whole theory versus what you can actually measure in practice, but let's just say it's below what your scales are likely to meaningfully measure with any granularity. You might see a gram or 2 drop, I mean you might even see 5 if you're lucky, but this could be rounding, it could be repeatability of your scales, stray neutrinos, I don't know, is that a thing? But you get my point. Many people have done videos about drying filament, and they've tried weighing the filament before and after. I think by and large they don't have a lot of success. They all find pretty soon that you can't readily detect the before and after weight, but we do think laterally around here, and what you can do is what I did here. I weighed the filament and the sachet before sealing them together in a closed box. Just like before, no water can escape that system. Then you weigh the sachet after, and whatever the increase is, that has to come from the filament. Now I might hear you yelling, what about the air? Because there's actually some air in that box. Way ahead of you. I did the maths, I worked that out, and I subtracted it. Nice idea, though. So, drying filament cold with a desiccant, yeah, that's a thing. That actually works. I didn't have the patience to run the experiment for days, but yeah, it does work. Moisture was removed from the filament, and that by definition is drying the filament, and not by a bad amount. And everything we've learned so far will tell us that as long as the silica gel retains that low relative humidity in the air, that drying will continue. There's no catch here. It's just time. The second part of this experiment was to put the same reel and the same silica gel into the Sunlu dryer and seal all the vents, because the lid on this thing is airtight and there's plugs and stuff. We'll look at that in a minute. But yeah, in the same kind of time frame, we got a lot of extra moisture out of the filament, and that was at 50 degrees C for PLA and I think 55 for ABS. And that is even given the fact that the silica gel doesn't work that well at 50 C and above. Its efficiency is a lot lower at higher temperatures. Probably actually a little bit more moisture got out because we're circulating air around. There's going to be some cracks in the base of the dryer when it's in this mode. That's a good thing. But yeah, the point is that what we've proven here is that adding heat into the mix, the same process happens more efficiently, or rather faster. So what's left to explain? Well, the vented dryer problem. You can dry silica gel in a filament dryer just as you would expect, having understood everything so far, but there is one missing link, I think. When you heat filament, or silica gel, what you're doing is evaporating the water out of it. You're increasing the energy of the water molecules, and in turn, they are turning into gas, and, well, leaving. If you carry this air away, then the process can continue with new unsaturated air until the filament or silica gel is in a much drier state. If you don't vent this, however, that second part is not happening. You're hopefully going to understand that in your sealed closed system, you're just You're just moving things around. The air will become saturated with water, you get condensation, and that is not a good sign if you've got condensation. And then when all this cools, the moisture is going to go back into the filament again, or in this case, back into the silica gel. As I said before, I think we all intrinsically know and understand this. If we did just put silica gel in a small sealed box and heat it, we know it wouldn't dry. But I see so many people not applying this to a filament dryer. Some of the reason why is because the instructions don't always tell you to, or haven't in the past. But I did notice that manufacturers are getting better at that, so that's good. So where does this get us? I think we need to tie all this up into some kind of summary, so let's do that. Firstly, filament is affected by moisture. How much moisture it absorbs depends on the environmental relative humidity. Relative humidity is not a useful metric to use when you're actually using a filament dryer when it's on. All it's actually telling you is that the air is warmer. It doesn't serve any other purpose, really. You absolutely need to vent a dryer when drying, in all cases when you don't also have a desiccant in there. But to be honest, vent the dryer, put the desiccant in as well. Dry them both. Fourthly, indicator silica gel looks really cool. Fifth, this is just scratching the surface. It really is. This is a hugely complicated topic, and it's been hard to not only summarize it in less than an hour, but also to tie the narrative together. I think the theory is simple, but the consequences of that theory, they just kind of, they get really complicated. If you do take one thing away from this video, I want it to be vent your dryer. If you take two things away from this video, I want it to be silica gel looks really cool in macro. But I hope you take a lot more away. Let me know in the comments as always, and check the links in the description, and subscribe as well, do that. I will see you next time. Thank you for watching.